Welcome to Electrochemistry. This is part 2, and I am Ms. Bedrosian, and this time we are going to be taking a look at batteries and how they work. So, when in the same container, when there's a reaction, heat is generated. So when the molecules collide, there's usually heat that is generated. Yeah, and it can get pretty hot, as you can see. However, if you separate them into two separate containers, we get an interesting effect. It forces the electrons to move through a wire. And as you know, electrons moving through a wire is known as electricity. But you know it has to be a circuit. So it must be a completed circuit moving in a circle. All right, so let's take a look at this because this picture appears everywhere. It's a picture of a galvanic, also known as a Voltaic cell. You've probably seen this picture before and probably have wondered about it. So let's take an up close and personal look at this picture. So oxidation occurs at what we call the anode. Oxidation, as you recall, and this anode here is copper, oxidation is loss of electrons, oil rig. So copper will be losing electrons into the wire. You can see the electrons are moving away from the copper strip. As the electrons leave the copper strip, the copper atoms will turn into copper ions and they will enter the solution because there's water in the solution and the water molecules will dissolve the copper 2 ions. And you can see that they will enter into the solution as the electrons leave the copper. So what happens to the copper metal strip? That's my question to you. What happens to it? Should be able to describe that. Now the voltmeter measures the movement of the electrons through the wire. It is not a battery. A lot of people think, oh, I'm putting this on and it's causing this to happen. No, the voltmeter is just measuring it. It is happening on its own. It is not a battery. It is measuring the movement of the electrons through the wire. Reduction occurs at the cathode. They both start with a consonant, so maybe that'll help you to remember oxidation anode, reduction cathode. Reduction, of course, oil rig. Reduction is gain of electrons as the wire is connected to both. The electrons are moving towards the silver strip. So you can see by the arrow that the electrons are moving towards the silver. Now the silver strip happens to be in silver nitrate solution. So there are silver ions dissolved in that solution. As the electrons move down the silver strip, these extra electrons, they will actually move down and they will actually come in contact with the silver ions that are in the solution. And when that happens, what do you think happens? If the electrons come into contact with the silver ions, the silver plus 1 will gain an electron. At that point, can you predict what happens to the silver metal strip? So you should be able to say something about both metal strips, because something will happen to it. Let's take a closer look at the solution that the copper is in. That's in a potassium nitrate solution. Neither of those participate in the reaction, but they do have charges. And that allows them to move across the salt bridge. So ions, the potassium ions and the nitrate ions will move according to maintain the balance on the overall charge between the two containers. To keep this going, it's allowing the circuit to be completed. So the oxidizing agent pulls electrons through the wire. In this case, it was silver. It was actually pulling the electrons towards it. This is also called the cell potential, also known as E cell. It's kind of a curvy E. I can't make that on this program. It's also called the electromotive force. And it's also referred to as EMF, which is short for electromotive force. So all of these are interchangeable. It is the act of the oxidizing agent pulling electrons through the wire. The unit for this is a volt. It's 1 joule per coulomb. Coulomb is a charge. You remember we've seen that before. And all of this is based on hydrogen. Hydrogen was given the arbitrary number of 0, basically. So 2H plus 2 electrons yields H2, and that was considered to be 0 volts. Now, all standards in the back of the book in the cells are given as reduction processes. I don't know why, but they're all just given as reduction. Obviously, these are redox, so half of it is oxidation. So in a reaction, one will need to be reversed. So you need to change the sign. You'll need to change the sign of the volts and change the reaction equation. And the value of E, or the electromotive force of the cell potential, is not changed when multiplied. That's kind of cool. It makes it easy. Don't have to worry about that. So for a very simple example, Fe3 plus Cu yields Cu2 plus Fe2 plus. Well, taking a look at that, we can see that redox is occurring. Now you need to write the oxidation and reduction half reactions and look up the EMFs in the appendix. Pause now. All right, here comes the answers. So first you're going to write the reduction half, oxidation half. Here's the oxidation half reaction. Cu becomes Cu2 plus, and 2 electrons are walking away, so to speak. It loses 2. And the reduction half, reduction is gain. So Fe3 plus 1 electron becomes Fe2 plus. And if you looked up their cell potentials in the back of the book, this is negative 0.34 volts for the oxidation half. I know in the book you have to be careful. This equation is given in reverse, so we must change it and change the sign as well, because they give everything as reduction halves. The other one we do not have to change. That's 0.77 volts, so that can stay as is. Now, we can add these together, and when you add them together, you do have to get the electrons to cross out, so you'll have to multiply. So 2Fe3 plus Cu yields Cu2 plus 2 Fe2 plus. But you don't multiply the voltages, so that's 0.43 volts is the difference. And part 2 is done. Welcome to Electrochemistry.